Alright, here's some homework problems. First set from Chapter 7 about energy and work and stuff like that. So, quick review of what we know so far going into this homework set from notes. We know, we have defined now that the kinetic energy, I'm going to use a capital K for that, kinetic energy of an object is 1/2 its mass times its speed squared. Now, we do use this V, maybe that's annoying to you a little bit. We use that V sometimes as velocity and sometimes as speed. Here, this is just the speed. It's the directionless version, which means that kinetic energy has no direction. It's just a quantity. It's always positive. You can't have negative kinetic energy. And it's not a vector, right? It's just a quantity. It's directionless. Energy is energy. We also know that work, the idea of what work is, which is very important to try to get your head around, is work is energy that's either transferred into or out of a system. Positive work if it's energy transferred in, if the net result is an increase in energy, and negative work if the net result is a decrease in energy. So work is equal to force times distance times the cosine of the angle between them. And you might remember that the cosine function is the one that shows up in the definition of the dot product. So it's the dot product of those two things, which means force times just magnitude, and that's the cosine of the angle between them. If they're going in the same direction, of course, the cosine of 0 degrees is 1. If they're going in exactly the opposite direction, like if the force happened to be a frictional force exactly in the opposite direction of the displacement, then that would be 180 degrees between them. That'd be -1. And you get negative work there. And we also know, doing some fancy little bit of calculus, that the net work done on a system is equal to the change in its kinetic energy. So if you have multiple forces, each one of those forces might be doing some work. There could be some positive work, some negative work, but you can figure out the net amount of work that's equal to the change in kinetic energy. And might also add up here in our definition of work. This is for a constant force. And when F is not constant, then work is equal to the integral of force as a function of x dx from one position to another. And we talked about that in class, and I think we will need that a little bit later for some of these problems. We'll see. All right, so let's get started. Number 1. This first problem, if you look at the little section titles, this is really just about kinetic energy. It's really just about taking this for a spin. So I've got a proton as a mass of 1.67 times 10 to the negative 20. Of course, they didn't have to tell you that. You just knew that, right? From chemistry or something. I don't know. That's out there. Is being accelerated along a straight line. And the acceleration is 3.6 times 10 to the 15th meters per second squared. You cannot maintain an acceleration like this for very long, can you? Because in, let's say about half a second or so, certainly much less than a second, you would be exceeding the speed of light, which is 3 times 10 to the 8th meters per second. So watch out. If the proton has an initial speed of 2.4 times 10 to to the 7th meters per second, and travels 3.5 centimeters, which is 0.035 meters. Then what's the initial speed? Oh, sorry, I guess it's final speed. So they're asking for an A. What's its final speed? And then what's the increase in kinetic energy? All right, well, this looks awfully like kinematics, doesn't it? So here, Vf squared is equal to Vi squared plus 2A delta x. So Vf is equal to the square root of Vi squared plus 2 times the acceleration times delta x. Let's jam that into the calculator, see what we get. Can you see that? I think you can see that. So the square root of 2.4, I'm going to use this scientific notation feature here, that raised to the second power. The calculator does understand that that doesn't mean 2.4 times 10 to the 49th. It understands that this is a number squared. That's how it processes order of operations in that case. And 2 times 3.6 times 10 to the 15th times 0.035, and syntax error. Great. What did I do? It looks like I have a stray parentheses problem here. I think it's let me try to get that back here and see if we can fix that up. So the square root of 2.4 squared, 2 times 3.6. I guess that I should not have put this here. Let's try that. There we go. So that's 2.9 times 10 to the 1, 2, 3, 4, 5, 6, 7. 2.9. I said 2 and I wrote a 3. 2.9 times 10 to the 7th meters per second. Right? So it started at this speed, now it's going this speed. And that's the answer for part A. And for part B, they want to know what is the increase in kinetic energy. Well, let's see, the final kinetic energy would be 1/2 mass times velocity. The final velocity is 2.9 times 10 to the 7th per second squared. And the initial kinetic energy is 1/2 mass times the initial velocity squared. So let's see, so we've got 0.5 times 0.67 to the negative 27th times 2.9 times 10 to the 7th squared, and that's about 7.0 times 10 to the negative 13th joules. The initial kinetic energy, I'm just going to bring that same thing up and just change that to 2.4. That gives me 4.8 times 10 to the negative 13th. So the change in kinetic energy would be final minus initial. It looks like it would be 2.2 times 10 to the negative 13th joules. So it increased by that. The book has 2.1 there, so I guess that's just some difference from rounding. I'm sticking to my answer there. All right, so just kind of using that. I guess we had to figure out kinematics can always happen, right? Next, we have number 3. And let's see, we've got a large meteorite skipped across the atmosphere. Yada, yada, yada. The meteorite's mass was 4 times 10 to the 6th, 4 million kilograms. Its speed was about 15 kilometers per second. That's 15,000 meters per second. As they would say in Ireland, that's pretty fast. Had it entered the atmosphere vertically, it would have hit the Earth's surface with about the same speed. So in other words, the old atmosphere isn't going to slow that thing down too much. So I think we're talking about dinosaur type situation here. Calculate the meteorite's loss of kinetic energy that would have been associated with a vertical impact. Well, the loss in kinetic energy, it's going to go from having all of the kinetic energy associated with this to hitting the Earth and not moving anymore. So it's going to lose everything. So delta kinetic energy is the final kinetic energy minus the initial kinetic energy. The final will be 0 minus 1/2 because it's not moving anymore. It has impacted the Earth, not part of the Earth. So let's see, mass times velocity. I put my units in there just to be consistent. Squared. So let's see what we've got here. We've got 1/2 for 6 times 15,000 squared. So that's a loss of 4.5 times 10 to the 14th, or 450 trillion joules. It's a lot of energy. So if that's kind of depressing to you, that someday a meteorite like this will in fact be headed toward the Earth, and we better have figured out what to do about it. If that's just too much to think about, you should probably stop doing the homework now. Part B, express the energy as a multiple of the explosive energy of 1 megaton of TNT. So 1 megaton of TNT has an energy of 4.6 times 10 to the 15th joules. So it's this as a fraction of this. So I've got that divided by 4.2 times 10 to the 15th. So it's about 10.7% of that. Or the book has 0.1 megatons of TNT, so same thing. C, the energy associated with the atomic bomb explosion over Hiroshima was equivalent to 13 kilotons of TNT. So 13 kilotons of TNT, so we have to do a little bit of a conversion here. We have 13 kilotons of TNT, and we want to convert that to how many Hiroshima bombs. So in other words, I guess this is maybe the wrong conversion, isn't it? I guess we should do, let's see how we should think about this. This is how much energy we have. 4.5 times 10 to the 14th joules. If you're wondering where the negative sign went, I'm just trying to figure out how much energy this is. This is how much the meteorite would lose, and since energy is conserved, that means that that energy is converted into basically destruction. So this is the energy associated with that impact. The meteorite loses it, and unfortunately we, the Earth, gain it. So that's how much we have. And we know that that's that 1 megaton of TNT, there might be an easier way to do this, I don't know, is 4.2 times 10 to the 15th joules, right? So now we've got it in megatons, and we know that I want to convert it to kilotons, right? So megaton is 1,000 kilos. Mega is 1,000,000 and kilos 1,000. So 1 mega is 1,000 kilotons. You could do that as 2 steps if you want to, depending on how you feel about that. So megaton, that's kiloton, and then I know that 13 kilotons is equal to 1 Hiroshima bomb. Hiroshima bomb. So that should convert this many joules into the equivalent of Hiroshima bombs into that unit. So let's see. Run that through. Got 4.5 times 10 to the 14th divided by 4.2 times 10 to the 15th times 1,000 divided by 13 times 1,000 divided by 13. So about 8.2 atomic bombs. And yeah, the book has 8 bombs, so approximately 8. So there you go. If you found an easier way, if you kind of reasoned through that and you didn't quite set that up, that's fine, of course. That's a pretty methodical way of doing it, I guess. Consistent with dimensional analysis, things that you have learned. All right, number 9. Let's see, can we fix that? I think we can fit this in here. So 9 looks more difficult than it really is, I think. There's only one force acting on this, right? The only force has a magnitude of 5 newtons. Now, if there's only one force, that means that, going back to our initial ideas, that the net work is equal to the change in kinetic energy. That's it. And energy doesn't have any direction, so here the change in kinetic energy is 1/2 mass times the final velocity is 6 meters per second squared. And I should say final speed, right? We don't care about the direction when we're calculating kinetic energy. Minus 1/2, 2 kilograms times 4 meters per second squared. And that's just 36 minus 16 is 20 joules, an increase of 20 joules. Energy does not have any direction. So all that stuff, like the magnitude of the force and all that positive x direction, y direction, that did not matter in this calculation. And I think that that's one thing that we want to try to understand and take away from this problem. It wasn't as hard or as complicated as it might have looked initially. Or finally. So number 13, a luge and its rider with a total mass of 85 kilograms emerge from a downhill track onto a horizontal straight track with an initial speed of 37 meters per second. We have a slowing down force with an acceleration of 2 meters per second squared. What's the magnitude required for the force? How far do they travel? What work is done on them by the force? And what are F, D, and W if they instead slow down at 4 meters per second squared? All right, that's a lot of parts. I think I need a new sheet. All right, so 13. We have the luge and rider have a mass of 85 kilograms, and their initial velocity coming out of the track is 37 meters per second. In the first 3 parts, they're going to slow down. If I say this is positive and they're slowing down, then this acceleration must be negative meters per second squared. And what magnitude F is required for that force? Well, force is equal to mass times acceleration. So if that slowing down force is the only force acting, if that's the net force, of course there's normal force and gravity, but if the frictional force is the only thing slowing them down, then the magnitude of that force, well, that force would be the mass of 85 kilograms times the acceleration. So that would be 170 newtons. We get a negative here, right? What does that negative mean? It means it's opposite to the direction that they're going in, right? It would be a force opposite to that direction. So the magnitude of that would be 170 newtons. So the magnitude of the force, you can use absolute value signs here like that, you know, to do magnitudes, just like we do magnitudes of numbers. That's what absolute value is. Part B, what distance do they travel while slowing? You could do that using kinematics if you wanted to, but we're going to do it instead. If you did that, that's fine, but check this out. The magnitude of the force, since it's a constant force, I know that work is equal to change in kinetic energy. Now the work is all done, net work is equal to change in kinetic energy. This is the only force, so that force, negative 170 newtons, work is equal to, if it's a constant force like it is here, then work is just equal to force times distance. That negative is important there. It's negative work that's being done. Change in kinetic energy. The final kinetic energy is 0, right, because they're stopping, minus the initial kinetic energy is 1/2 mv squared. So this is kind of cool, I think, to see how you can find something that we would have done before with kinematics. Now we can do it with the work kinetic energy theorem. Now the way to understand this equation, I think, is that friction is like tapping all of the energy out, right? It's taking all of the energy away from the system. Negative work. All right, so it looks like the distance would be equal to 1/2 times 85 times 37 squared divided by 170. So the amount of work done, the distance is 342 meters. And that agrees with the book, just checking. And part C, what work is done on them by the force? Well, the amount of work that's done is force times distance, so that's negative what we just got times 170. And you could also have got that from this side of the equation, right? So about 58,000 joules, negative 58,000 joules. And then parts D through F, it's the same exact calculations, except if you double the force, if you double the acceleration, that's going to double the force. So let's look at our relationships and see what that's going to do. Here, doubling the acceleration, that would just double the force. So, nothing's getting squared or anything here, it's just a linear relationship. So that would double. In part E, again, we've only changed the force, right? So if we double the force, that's going to double this. We're going to divide by something that's twice as big, and it makes sense that if that acceleration were greater and the slowing down force is greater, then this would be cut in half. So that'd be about 171 meters or so. And then F, again, we would have force times distance. And that, notice, actually is the same, isn't it? Because we still tapped all the energy. The initial amount of energy is still the same thing. So that's not going to change the answer for F. Because that force, even though it does it in less distance, it had a greater magnitude, and the total amount of kinetic energy that we had to zap out of the system is the same. So that part will be the same. Just check, make sure that I haven't given you any misinformation there. That looks like it's all the correct answers. Except, yeah, that's all right. Number 34. So this is a couple problems, work done by a variable force. So we should be thinking here, work is equal to, so if the force is not constant, instead of just force times distance, we have to do the integral. So let's see what we get here. 34. And if this is like news to you, you're like, oh, right, then pause here and go back and try these problems again. Number 34, a 10-kilogram brick moves along an x-axis. Its acceleration as a function of position is shown in figure 737. The scale of the figure's vertical axis. I'm going to make a little copy of the graph here. So here we have an acceleration of 20 meters per second squared, and here this is 8 meters. Right? It's a variable force, right? So it seems like the further you go in this situation, the more acceleration and therefore the more force there is. This is acceleration, this is displacement. Meter is meters per second squared. And I'm going to stop right here before I read any more and just point this out. You have to understand here that since this is acceleration, if I multiplied this by mass, this is basically a graph, although with a different scale here, of force versus distance. So if I multiply this by mass, that's equal to net force, right, which would then be in newtons. So then that would turn this 20, since the mass of this thing is 10 kilograms, that would just rescale, so this is 200 newtons. So I could take this graph of acceleration versus distance and say, hey, that's just basically a graph of force times distance if I multiply this axis by mass. And then that should make this very easy to do, right? Force is a function of distance, dx. And again, I'm going to point out that notice this is not force as a function of time. This is not, in calculus, this is like a dummy variable. Here it's not. These are positions, right? So I guess even if this was a dummy variable, we're plugging positions in here, right? So you cannot do this with a graph of force as a function of time. You can take that integral, but it means something else that we'll learn later in the year. All right, so let's see what they want to know here. What's the net work performed on the brick by the force causing the acceleration as the brick moves from 0 to 8? Well, that's just the integral from 0 to 8 meters of this force function. I'm not going to try to write an equation for it and do calculus because this is such an easy geometry problem. You could find an equation for that line. It's not hard to do, and you would get the right answer. But it's just the area of this triangle. So 1/2, that would be 4, so that's going to be 800 joules. And so if you understand it in that way, that's a pretty easy problem. Number 37, looks like we got another, it's a similar graph kind of situation. I'm going to do the same thing and recopy the graph. But instead of an acceleration axis, I'm going to turn it into a force axis by multiplying by the mass. So let's see, what's the mass of this thing? It's 2. And the scaling is, it looks like it goes 6 to -6. So instead of 6 to -6, since the mass is 2, force equals mass times acceleration, that's going to be 12 newtons to -12 newtons. I don't know why I put that in parentheses. That was weird. So 2, 4, 6, 8, then at 9 it's here, and then this is at 5, and 4, and so made a decent job of this. This is looking awfully geometric too, isn't it? So this is 2 by 12, and this is 3 by 12. And those little triangles are whatever they are. That's one, I guess those are all 1 by 12 triangles. So I'm just going to fill in the areas because I know that's coming, right? So this is an area of 1/2 base times height, that would be 6. This is 3 by 12, that's 36. This is 6, 6, 24, and 6. Right? Okay, what do they want to know? They want to know how much work has the force done on the particle when the particle reaches 0 meters? From 0 to 4. So we're starting at 0. So that would be from 0 to 4 meters. From 0 to 4 meters. Well, that's awkward of them, isn't it? So this is 1, 2, 3. 4 would be here. So that would be 24 and 6. I think that's 30 joules, right? You can check that. B, 7 meters. Oh dear, they didn't give us where's 7 at? Well, 7 I guess is here, halfway between this and this. So this is negative stuff underneath. So that negative, that's going to cancel out this much of it. Oh, so that's also 30, isn't it? I think that cancels out to be 30 as well. Let me just check that. It does. And C, 9 meters, that's like all the way, so that would be, looks like just 12, positive 12. Everything cancels out except for positive 12 joules. D, to 4. Oh, sorry, what is the particle's speed and direction of travel when it reaches 4, 7, and 9? So, what is the initial acceleration particle from rest? Okay, so its initial velocity is 0. So that means if work is equal to the change in kinetic energy, net work, which is this, then in part D, there was a network of 30 joules was done. So that means work is equal to change in kinetic energy. That's 1/2 mass times final velocity squared. And the initial velocity is 0. It starts from rest. So that looks like the square root of 30, whatever that is, meters per second. They don't probably want the answer like that, do they? The square root of 30, about 5.5 meters per second. That's how fast. You might notice here that this is all positive force, so all through here the object is going to be speeding up, right? And all through here the object is going to be slowing down. But notice that we never end up in a situation where we have negative work, right? All of this positive, we don't have enough negative that it's ever actually going to be negative work. So this thing is going forward the whole time, albeit speeding up and then slowing down, right? And part E, well, it's the same amount of work done, so that's not going to change this equation at all now, is it? So that's, oh, wait a minute. They have 42 here for this first one. Now maybe I made a mistake here based on my fairly substandard graph. Is this, what did they want? 0 to 4. Oh, I guess I missed that was 4 there. I saw that 3 and I thought that was 3. So sorry, this should be 42. That's where 4 was. This was 5, this was 6. So that's going to change. So this is the right answer for E. And then here it would be the square root of 42, right? The calculation looks the same, but be the square root of 42, which is about 6.5 meters per second there. And then last, the calculation is going to look the same, right? And you can see here it's still positive area total, so it's still going to be a positive answer. So that's just the square root of 12, which is about 3.5 meters per second. Cool. There you go.